access control lists. This is a common weakness that we'll encounter when we're doing red team and hacking because ingress filtering is not deployed or it's not deployed properly. Ingress filtering is inbound traffic controls. We should have all inbound traffic sourced from an external address, and Cisco's and other routers have a thing called the established keyword. The access lists that are stateless only knows the contents of the current packet it's processing. So what we can do is we can trick these types of devices into thinking they have a connection. If we trick them into thinking they have a connection, it gives us the capability to penetrate the actual filter itself, which is a weak access control list. And it's what we call the ACK flag set. So what that is the acknowledged flag being set, it looks like return traffic. The stateless filter only looks at traffic of the current packet. It doesn't know if a request went out or not, and it allows us to get through. And we do it with a technique called source port scanning that we will cover. Egress filtering. In the egress environment, an access control list should only allow traffic to leave the network that has the source address of the network itself. What we do when we do our testing, if we compromise a box, we try to see if we can egress out and use a source address different than the actual inside network. And if it does come out, that shows us that we've broken the egress rules on that environment. So we got a graphic here, and we're showing you an actual diagram that says that hypertext transfer protocol. It's HTTP, web. It's web traffic. But if you look at the diagram that says follow TCP stream, does that look like web traffic? No, that's FTP. That's FTP traffic over HTTP. But the problem is in the actual addressing. In the addressing, when you look at it at the time of this slide, the 223 address was not allocated. So this organization's not doing proper ingress filtering because it's allowing an unallocated IP address as a source address to talk and communicate with its network. So what we do from the hacking standpoint, red team hacking, we will spoof or source our address of something that we know is part of what we call a balgon or a filtered list of bogeys. And if we get a communication, a SYN, SYN-ACK, ACK, the three-way handshake, that means that source address was allowed. That means that organization is doing poor ingress filtering, and now we have source addresses we can use that won't be monitored or tracked by their monitoring devices in most cases. So what exactly is a firewall? Well, it's our next device. If we covered the routers, we covered the switches, what's our next device? It's the firewall. Well, a firewall kind of is a bad name because a wall means it's solid. A firewall is not solid. We took a solid device and poked a bunch of holes in it. But anyway, it's with what we got, it's the name. The firewall is designed to protect the trusted side from the untrusted side, or the heat of the internet from the internal network. It's a gate, basically. A firewall is a gate because you configure it, defenses configure it, to allow services or ports through it. Our goal as the hacker and the red team is figure out what's allowed through the firewall, and we use that as our vector to potentially get to the other side of the services into DMZ and attack there. Once through it, we don't need to worry about it anymore. It's just a gate. So we got some types. We talked a little bit about a router, and an access control list is what we call a stateless firewall. When we're doing our testing, we want to know if we're up against a stateless firewall, because stateless packet filters or routers only understand the concept of the packet that it's currently looking at. Okay? It usually blocks or passes traffic based on some combination of information within the packet, usually the IP address, the port number, or the flags in the transmission control protocol, TCP. It's a cheap protection and a useful level of security because it's free. It comes with the router and it's free. It requires an administrator to make a list of acceptable hosts and services. Stateless packet filters have no concept or memory. So what they do is they only look at the concept of what am I looking at currently. And that's the problem with the stateless packet filters, protocol problems. Several protocols and application services pose problems for these stateless filters. What about fragmentation? If I have a bunch of fragmented packets, what's the stateless filter going to do? How's he going to know which packet goes with what? He doesn't. He doesn't have memory. Protocols without a fixed port number. So a port's our door into a system. So a stateless filter has to know what door that port is going to be allowing that service every time for the rule to take effect. So it's a problem with that. And then file transfer protocol in X11, which allows return connections. It has a client of a client and server type connection. So it's hard to control these with a stateless packet filter. From our hacking standpoint, the router is a stateless packet filter. We will do a series of techniques in our methodology to figure out what the router allows and doesn't allow. Okay? DNS. Dealing with DNS is one of the trickiest problems for packet filters. We don't want to expose the DNS servers to the outside. So the most common way we do with domain name server, or DNS, is we set up what's called a split DNS. Split DNS being we have a public-facing DNS that allows all the queries to the internet and back, and an internal DNS that all machines inside use the internal DNS to query to the outside, but it's a forwarder. It only forwards queries to the external or public DNS, and it doesn't have any information about that other than forwarding the data to it. The external DNS has no knowledge about the internal DNS, and in fact, give us split DNS as far as the information that each DNS contains. UDP, User Datagram Protocol. The problem with UDP is there's no concept of a connection. There's no flags. There's nothing in UDP. We don't know if the packet's coming or going. We can't distinguish between an incoming and an outgoing call. We don't have any header flags. It's connectionless. It's called connectionless because it has no concept of a connection. It's virtually impossible for these routers that are packet filters to handle successfully. So because of this, we have to look at a stateful packet filter. Stateful packet filters overcome many of the problems with stateless packet filters because they have memory. They have a concept. They know if a request went out to open a port, they know there should be a reply. If there's no reply, they close the port. So it's what we call dynamic port control because it'll only open the port for a dynamic amount of time. Okay? They also can deny or allow packets not only in the contents of the current packet, but contents of previous packets before it. They have an understanding of application protocols. They don't actually know what application protocols are, but they do understand them, and they can control reverse connections and vary port numbers. Then we have what's called an application proxy. If any of you ever voted by proxy, it's the same concept. Rather than actually do the actual application itself, a proxy, small purposefully written code running on the Bastion host or a firewall box that is going to act on behalf of the larger program. Sometimes referred to as an application level gateway. They're nice because they can actually stop a lot of attacks because when you run an application proxy, the vulnerability usually is in the main program. It's usually not carried over to the application proxy itself. They have deliberately limited capabilities, which makes it easier to make secure. We call it tightly coupled code in a programming world. Some proxies are free, some are commercials. We have an example here, Smoothwall, a nice open source proxy, and FortiGate, which is a commercial product. But a proxy will run and act on behalf of another program. So when we encounter these in our testing, it can make it a challenge because our application layer inspection is there, and we might have to go look at other protocols that encapsulate or wrap layer 7 application information. So what firewall architecture does an organization typically deploy? Well, it usually depends on their security requirements, their information services to be supported, and their expected traffic levels. A standalone router will, if packet filtering helps us, as we said, it does give us some protection, but they're there to route. Filtering is a secondary function. So purpose-designed packet filters are much higher performance and easier configuration and much better when it comes to firewall architecture. As I showed on the board a little while ago on the easel, there literally is, the flip chart, there is different architectures and firewalls. So you have to be aware of this when you're testing that you're probably going to run into a point of some type of firewall architecture. So most organizations are looking at high volume, as we said, external access to public information services, internal access to external services, and very restricted external access to the internal network. The most appropriate firewall for this is called a screened subnet firewall. We use a combination of a packet filter and a Bastion host. Okay? And this is an example here of a classic firewall architecture. So as you see here, we have our internet cloud, we have our packet filter and screening router, and we have our public DMZ. And then we have our bastion host. This method offers 2 layers of defense, being the packet filter and router is defense layer 1, and the bastion host is defense layer 2. The DNS server is set up with the external DNS in the DMZ and the internal DMS that the internal network only uses the internal DMS to send out queries. Well, here's some of the problems with this. And advantages of it first are the access to external services does not impact the internal network. The DNS server, as we said, split DNS, so the DMZ DNS has really minimal information about the network. The internal DNS holds the complete information isolated from external attacks by the application proxy. It's 2 firewalls, 2 layers of protection. Traffic through the application proxy is restricted to the proxies installed. We can't route through the application proxy, but all accesses are logged. Another advantage is traffic from the internal network emanates from a single IP address, that of the IP application proxy. So we can actually figure out, looking at our traffic, very quickly what is going on, because only one IP address should be in the logs. If another IP address is in the logs, we've been compromised or our architecture is not acting like it should. But from the attack standpoint, it's good news, because if we compromise the bastion host, we use that to attack the internal networks. But these are the types of architectures you will probably encounter. Typically, this architecture is combined into one appliance, like a Cisco ASA, for instance, the Adaptive Security Appliance. The Cisco ASA has inside of it a DMZ, the router capability, and the stateful packet filter capability, all within the appliance itself. So effectively, the 2 layers of defense is inside the Cisco appliance internally. Then we've got what we call the belts and suspenders firewall. Because if the bastion host gets compromised, we can get to the other side, we just put in another router to add a 3rd level of defense. So now we have our 1st level defense, the screening router, the DMZ, the public DMZ, the bastion host, and then our internal router, which is our 3rd level of defense. So now if the bastion host is compromised, there's a router protecting me. So it goes without saying, regardless what vendors try to tell you, that screening router and the internal router should be different vendors. Because if I get a vulnerability in the screening router and it's the same vendor on the internal router, why have the internal router at all? It's the same vendor, same vulnerability, I get access the same way. So always remember, in a defense standpoint, you should protect yourself. So what do we do in perimeter configuration? We know most organizations are do what we call sanity checking. They're ingress filtering. We cannot have a source address of the internal network. So the first thing we do when we're testing this from a red team standpoint, we spoof the address inside of the router. If we get communication, send, hacker, we get anything, any accepted packet, we know they're not doing proper sanity checking. In outbound packets is egress, as we said. We cannot have a packet leaving the network with the address of anything but the inside network. If they allow that, then there's a problem there. Another thing a perimeter configuration can do is geo-IP blocking. They might set up geo-IP blocking and block entire countries. So we need to test that as a red team, depending on the location we're doing our red team attack from. And then finally, a perimeter configuration that's properly configured will always have a default deny, which is the prudent approach to security. That means anything I don't know, I'm going to deny it. So we have to be conscious of that when we're doing our red team hacking. So what do we do with firewalls? Can we attack firewalls? Well, they are software like anything else. There's been bugs in software of the firewalls. Firewalls have vulnerabilities too. We got to get the type of firewall. Possibly they'll have a default port open, but most firewalls should make this difficult. When on the untrusted side, we shouldn't get any information back. Usually a firewall, if it's a good firewall, will not talk to the untrusted side. Identify the services allowed and attack them. That's what we do in a firewall attack. We figure out what the firewall allows in, and that's what we attack. That's why we follow a structured methodology as a red team. We're going to hack based on the structured methodology and find what lets us in. The services might be the only way in. I once participated in a team, and we compromised in a short period 3,000 hosts all over port 80. That was the only port allowed in by this organization. But over port 80 to those services, we were able to find enough vulnerabilities and leverage those vulnerabilities to compromise 3,000 hosts. So when you're doing red teaming, one access point is all we need, one port in or one service in, to be able to compromise the entire architecture. The only port was open was port 80, but it was enough. And that's the important thing to remember when you're doing a red team hack, is follow that structured methodology and process and find the vector of that one way in. We get one way in, we win. It's fun to be on offense. Now we're going to do a lab here on device attacks.